Down by my house is a little river. It's a beautiful little creek or something. And if you wade in it at a good day, the water might come to your knee or your waist or something like that, depending on the rain. When I go down there, I like to put my feet in the water and feel the flow of the water going by. In AP Physics, we think about the definition of what water flow is. The flow of the water is the volume that moves per second. The formula for flow is area times velocity. Now this area is like the cross-sectional area of the water. So if you were to imagine this river and you take a slice of the side of the river and look at that slice, that's the cross-sectional area. Let's assume for the sake of simplicity that the cross-sectional area of some river, the river I'm talking about, is just a square or rectangle like this. So this here is the cross-sectional area of the river. Maybe it's flowing that way, kind of into the board there. So the flow of water is the cross-sectional area of this times the speed, the velocity of the water. So if we were to measure how quickly the water is moving, we could measure the speed there. So the flow is the area times the velocity. Now the units for flow are going to be meters cubed per second. So really it's about a volume of water that goes by a certain mark per second. And if we think about the units, area is meters squared and velocity is meters per second. So together they make kind of a volume of water that travels per second. All right, let's imagine a pipe system with water in the pipe flowing. So the water in these pipes is moving this way. And here the pipe is a skinny little pipe, and the pipe opens out into a big fat pipe over this way. This part of the pipe has a small cross-sectional area, and this part of the pipe has a large cross-sectional area. And the question is, where will the water be moving faster? It's moving to the right here, and it's moving to the right over there. I don't know if you can sense the answer, but the answer is it will be moving very slowly in the large pipe, and it will be moving very quickly in the skinny part of the pipe. There's an important formula that says the flow of the water in one part of a pipe is going to be the same as the flow in another part of the pipe. So the cross-sectional area times velocity here is equal to the cross-sectional area times velocity here. So as the area gets larger, the flow stays the same. The amount of volume per second stays the same. So the velocity has to get much smaller to compensate for that. Let's do an example calculation. Let's say this part of the pipe has a diameter of 0.5 meters. This part of the pipe has a diameter of 4.5 meters, a way larger diameter. So we can calculate the cross-sectional area of these. They're both circles. This one is a little circle with radius 0.25. This one is a bigger circle times 2.25. To calculate the areas, we use our circle calculation, pi r squared. I get 0.2. And for the bigger circle, so for the little circle, I get 0.2 meters squared. And for the bigger circle, I get 16 meters squared. So this is quite a lot larger. So we could calculate how much faster the water will be here than there, or how much slower the water will be here than there. We say A1 times V1 is A2 times V2, and let's do it this way. A1 divided by A2 times V1 is equal to V2. That is, there's a ratio, we call this a step down ratio, because this area is getting larger, which will cause the velocity to step down. So I get 0.125 times V1 is equal to V2. Or if I put on the other side, it's saying that it's 80 times slower than V1. So the velocity here is going to be 80 times faster than the velocity here. And that's going to be 80 times slower. The best way for you to improve your grades is with a practice test. On my side, I have some free practice tests on the topic of fluids for you to get. Click the link below to get a free practice test. One of the ideas inside this concept is the incompressibility of fluid. What we're saying is that the flow of the water is the same everywhere in a pipe. The volume of fluid per second is the same everywhere. So if the cross-sectional areas are changing, the velocities are going to change with it. And the idea of incompressibility is saying that there's no loss of flow when we squeeze it into smaller or expand it into larger spaces. The flow of the liquid is going to be the same everywhere. Let's do another example about flow rate using a waterfall. Let's imagine there's a river of water flowing this way to a cliff. Now the water falls down there. We could say that the speed of the water is 15 meters per second, and there is a volume of 2,000 meters cubed falling every second over this waterfall. It's a big waterfall. Let's imagine that it has a certain width. Let's say it's 25 meters wide. The question is, what is the height of the water in the river? That is the thickness or height of the water at that part of the river. The way we do this is by thinking about the water as a cross-sectional area, like a rectangle. If we were to look straight at the water, the cross-sectional area, this would be the water there. It has a width of 25 meters. The question really is, how high is this section there? To figure out this height, we've got to think about the flow rate formula. The flow of the water is the cross-sectional area times the velocity. Now, for area, we're going to go height times width, and we know the velocity. So we can solve for the height. And there we go. The flow is the 2,000 number, and we can plug everything in. So what's the height of the water going to be? The height of the water is going to be 3.2 meters. That's how tall or deep the water is going to be. Have you ever thought about the speed of water flowing through pipes or a river before? Or do you have any questions about this flow concept and flow formula? Type your questions below. I read every question.